Okay, we are back. I'm going to continue this 5G session. I'll be kind of continue where Dean actually kind of talked on this from an other point of view. I'm going to touch on 5G more from a transport network requirements and architecture to actually provide transport for 5G traffic. So I think Dean kind of touched on obviously, some of the figures where we basically see that by 2025, we are going to have 2.6 billion 5G subscribers connected. This obviously puts some demand in regards to the next generation transport networks. So I'm basically going to spend, the next 15 minutes trying to at least give you a high level overview of the challenges to transport 5G traffic. And Dean kind of alluded to some of the 5G kind of applications or services. So there shouldn't be anything new in that sense, but obviously we have the mission critical services. We have things like autonomous cars, and then you go into the massive IoT, which Dean touched on as well, where you basically provide connectivity for a new wave of device types. And then you go into both the fixed and the mobile broadband. And as we heard in the previous presentation, obviously you have things like increase in bandwidth to 10 times bandwidth per connection, low milliseconds latency, 5 nines reliability, and 100% coverage, so on and so forth. So I think this kind of sets the ground for how and in what manner you should actually transport this traffic. So to kind of take a step back here and for all of us to understand where the challenge is here. Now, if you look at the current 4G kind of architecture, so what you'll have is a couple of big data centers where you basically then obviously have all your applications running for your mobile network. Now with 5G, this is going to completely change. You're actually going to go into a thousands of small micro data centers, which basically means that the architecture is going to change. And this is due to the fact that if you look at one application, just to pick one, which is many times talked of, which is basically the autonomous cars. So if you look at the current 4G, with a few cloud data centers, now you have a scenario where you have a car driving. If you would actually have this deployed in a 4G network, you would actually look at more than 80 milliseconds latency to basically get a response back, which would mean that the car would move over 4 feet during that period of time. Now, if you compare that to the 5G, where you would have these thousands and thousands of small micro data centers, the same scenario would actually mean that you have less than 5 milliseconds latency, which translates into the car would move less than 4 inches by that time. Hence, this is kind of one of the fundamental things, obviously, with 5G. Now, to basically add to that, the NFVI architecture, how you actually build up this. Today, obviously, you have, everything is virtualized. You have VMs running your applications. And, going forward within 5G, you would have containers doing the same thing. And that basically means that all of the applications, so be it the 5G core, the EPC, the IMS, the virtual RANs, as said, 5G is cloud native, which basically means that all of these application services are going to run virtualized. So you can imagine that you still need to have a transport network in place here. So taking this a step further, now as the network architectures transition to cloud-based connectivity and obviously software-defined networking control for those ones, I'm just picking one example being the 5G RAN, which is a virtual service, as I mentioned in the previous slide. So service providers are able to actually dynamically support a range of use cases with varying demands using SDN control and orchestration. Moreover, with the advantage of running virtual network functions, as I kind of showed in the previous picture, any open hardware like the various data centers that I kind of mentioned being a fabric is truly needed here. So with that said, let's actually move on to the next slide. This kind of shows you the 5G service enablers. We touched on a few of these. Obviously, you have the millimeter wave, you have the new channel coding, you have the 6 gigahertz massive MIMO, you have massive connectivity with the IoT things. But a couple of things I kind of want to point out here is the low latency networks, which I kind of previously showed in my example being, the autonomous cars, which basically have a demand on how you transport that network, that traffic. And then another aspect is obviously network slicing. So if we actually look at the network slicing part here, what it basically means is that you need to handle the tsunami of device-to-device communication that is expected with 5G. So the next generation networks will require, denser RAN architectures, amongst others, with distributed intelligence. And this is increasing the densification, which means more advanced topologies in the access part of the transport network, such as mesh or ring architectures, as well as an evolved front haul and back haul interfaces. So in addition to connecting physical radio sites, the 5G mobile networks need to support virtual network functions, as we saw on the previous slide, in order to enable network slicing and connect subscribers to the cloud-based applications, which basically means that you need to actually ensure smooth evolution into integrated 4G, 5G network requirements with scalability and things like that. So at the end of the day, this actually means that you have a network in place where you have multiple different applications, where you basically need to provide a network slice for a given application to be able to provide specific service level agreements or specific delays, latencies, things like that. So to basically look into this from the 4G to 5G network evolution challenges, what you basically have here is a 4G central RAN model compared to the 5G RAN model. What you'll have in place here is obviously on the 4G side, you had the back haul, you had the front haul. While when you go into the 5G part, you can see you have your back haul, your mid haul, and your front haul with different requirements. And as you can see on 5G, you start to talk about some kind of synchronization in place where you actually have PTP, so 1588v2, as well as sync E being requirements. The sync E part is obviously more like backwards compatibility with current metro networks, things like that. But as we can understand, this is truly putting new challenges on how you would transport the 5G traffic. So to kind of try to explain this shortly in a single slide, this shows you the 5G transport platforms and technologies today, what you actually have here. So you basically have three key building blocks in this architecture, which is the centralized unit, which is the CU. You have a distributed unit, the DU, and the radio unit being the RU. So together, these three main functions, three main functional modules makes up the 5G base station, while the functions of the CU and DU were combined with the 4G baseband unit, so something called the BBU. Now, 3GPP, which is the 5G specification, introduces a functional split between the previous BBU design as a way to lower the transport cost and offsetting basically the significant increase expanded with the 5G transport rates. Now, the dual split RAN architecture is similar to the 4G BBU, where the DU resources are centralized in a pool for connectivity to RUs at multiple cell sites. So in this configuration, front haul provides connectivity from the DU to the RU. And since the DU are centralized, the resources can be pooled across multiple cell sites over the front haul spans. So this pooling capability enables the service providers to engineer performance demand for the RAN based on the region within the group of the cell sites, instead of based on individual cell sites. Now, individual cell sites performance engineering is very inefficient, since the dedicated DU cannot be dynamically scaled when greater performance is needed. Hence, you actually start to look at the cell site RAN architecture that offers dual functionality, providing low latency and centralized operation. Now you'll have the DU, RU, and the local CU users and control plane function, as well as the possible multi-access edge computing, the MEC functions. So you guys probably heard about the edge computing with the mobile edge. And all of these functions are co-located at cell sites to support latency-sensitive applications. And you basically have a second CU user plane at the edge site for centralization benefits. Now, to achieve dual functionality, you basically need to have a DU resource and sliced over fixed allocation to resources for each of the two CU user planes. So this is pretty complicated in that sense that you truly kind of need to look into multiple different parts within the network. As I said, you have different requirements for the back haul, for the mid haul, for the front haul, and how you have these different, the core network, the CU, the DU, and the RU. So as said, this is truly a short kind of high-level overview of many of the technical challenges you have. But basically where I want to kind of stop this one is to show you the 3GPP to the 5G blueprint of basically, how it builds up. And as you can see, the transport network is a key function within the 5G networks, even if you have a separate data plane, multiple control planes, things like that. So with that said, this was a true high fly in 10 or so minutes on truly some of the requirements for 5G transport networks. So to summarize, there's obviously a lot of things that need to be considered to transport 5G traffic. So I'm basically going to stop here. Any questions? If not, then I do believe that we have a break scheduled as the following thing. So the break, I believe, is 10 minutes or so. So thank you for listening to my presentation, and we go over to the break.